All right, so the last thing I want to cover here in this section is the movements in 3D. We're kind of representing them in the same polar-ish frame. And that brings us to cylindrical frame, which is the 3D or extension of polar frame into 3D space. Consider a particle that is moving along an arbitrary path in 3D space. What we can do, we can project the motion on the two-dimensional space. So that becomes the red trace. In the 2D frame, we can, same as before, oh, that's not good, find the radial and transverse axes. Very easily define the motion, the projection of motion in 2D space using a polar frame. The only thing we need to now define and add to our frame is a third axis and the distance along that axis to get to the actual 3D position of the particle. So everything remains the same. We have a 2D polar frame with one added dimension, that is the height, and that is our z. So if I want to define the position, velocities, and acceleration of the actual particle, position becomes r ur plus this z uz. Just give me 1 second to be messy. This vector plus that vector. And these are the two adding together to give me the total position vector. So let me clean up. That's that. Velocity similarly becomes simple. Essentially, everything we had in 2D, add the third dimensions. So before we had, I don't need this, r dot ur plus r theta dot u theta. Now we add the rate of change of height, z dot uz. And lastly, acceleration, r double dot minus r theta dot squared ur plus r theta double dot plus 2 r dot theta dot u theta, and adding acceleration in the vertical component, uz. So cylindrical is essentially polar frame, adding to it a z dimension or a vertical dimension. And everything essentially remains the same. Let me write it down. If you want to find the magnitude or magnitude of velocity or speed, that is r dot squared plus r theta dot squared plus now z dot squared. And magnitude of acceleration has 3 squares, r double dot minus r theta dot squared plus r theta double dot plus 2 r dot theta dot squared plus z double dot squared. All of it is squared. So that is cylindrical frame. Fairly easy, and it is a very good frame to describe movements when you have a strong rotation in a plane, in one plane, and movement going up and down. For instance, going around a spiral on a roller coaster, coming up, coming down, or going up. Let me draw it. This problem is extremely well suited if you have such a motion. There is a rotation and a vertical or third dimension component added to it. So okay, that is all we have for this section. I will wrap it up here, and there's just one other section left of this chapter. We cover it in the next set of videos, and we should be done with kinematics of particles. So I'll see you next time.